complicated title. So yeah, I am Fabio, and this is joint work with Paolo Baldi and Giuseppe Primiero from the University of Milan in the logic group. This is a short paper, so hopefully my presentation will be brief enough. So the motivation behind our work is depth bounded Boolean logic, which are well, logics that can reason up to a given depth, as the name may suggest. They are based on this type of truth tables that are non-deterministic. So basically, I would say that for so whenever the truth values are, at least one of them is a definite truth value, so it's true or false. They produce definite values as well. But when both parts of a conjunction or disjunction are undefined, basically you get a sort of non-deterministic behavior. So the classic example being the conjunction, so the conjunction may be both undefined or false in the case of conjunction. Because you may think of a classic example where you think of something that you either think it's a chipmunk or it is a mouse. So you know that it can't be the case that they are both true, right? So their conjunction is false. But if you think about another case where the two propositions here being considered are like, it is a mouse and it is in the kitchen, you may want to suspend your judgment about the conjunction. And similarly for the other connectives. So you get this sort of undeterminism. So it turns out this kind of undeterminism is captured by some tableau rules that are basically the classical ones, more or less. So you just syntactically manipulate the formulas in your theory. So you, for example, you can apply modus ponens, which is kind of a classical operation, syntactical operation, until you reach a point where you have to perform a cut. So a cut is a guess. So when we reach the cut, we have to guess whether some proposition, which is we are unsure about, is true or false. And then if we guess its value and then determine that regardless of whether that proposition is, for example, true or false, or that formula is true or false, then we conclude something, for example, B is true. Then we may conclude that B is true, given that theory, at depth 1, because we have performed only one cut operation since we start applying syntactical operations to our theory. So the basic idea of our paper, which is a short one, is to extend that to answer set programming. So in answer set programming, you have you can you can think of a tableau system as well that is described, for example, in this publication here. And then again, you have logical rules and a cut rule that again correspond to sort of guessing the truth value of some proposition in your language. Again, if you conclude something, you can derive, so well, in the case of ASP reasoning, you may not want all branches to agree on something, but you can consider that, for example, this branch to the right that you see here derives B. So B is basically derived from at least one of the branches of our syntactic derivation. And this is what we managed to make clingo derive from theories. So basically, a running example we have in the paper is that of Sudoku, where we start from a Sudoku. Apparently, a Sudoku needs some guesses. Well, some Sudokus need to guess the value for some cells in order to solve it. So basically, we showed that our implementation of clingo that we provided and we dubbed the k-lingo system may derive what an agent thinking and reasoning about a Sudoku at zero depth will think are the reasonable options for the values for a given cell after having performed k guesses, basically from the initial Sudoku. So from the initial values you had in the Sudoku. So interestingly, so for example, in this Sudoku, I've reported these gray digits, which correspond to what an agent reasoning at zero depth will derive as reasonable without having the capability of guessing anything. So it can't derive a full solution to the Sudoku, but it can nonetheless derive some information about it. Another example that I will quickly go through is the pigeonhole problem, where you have to map some elements from a given domain to some range. And in this case, a zero depth reasoning agent wouldn't even be able to understand that this theory is unsatisfiable, and in fact, it is only a one depth reasoning agent that can deduce that such theory is unsatisfiable.